All right. Hello, everyone. Welcome back to Historical Geology 1404. We're jumping into Module 3 today. Hopefully, you have taken Exam 2. If you have not, take it pronto. We are right up against Thanksgiving break. I will still be uploading the next lecture on Tuesday. If you are one of my high school students, you are not required to be here, but I will still be lecturing, and I will still be providing that lecture or that recording for you, okay? Let's see. After Thanksgiving break, we've got 1, 2, 3 more days to meet. It's almost the end, my friends. It's only a few more weeks to Christmas break. How crazy is that? So what that means is there are going to be a few days that, because we do have a Thanksgiving break in this semester, I will need to double up on a lecture. Okay, so and it'll probably be the last lecture that we do. I'll probably double up on it so that we can have a final exam review. Okay, I'll work out all that math after Thanksgiving break. Your final exam is going to be over everything. You are going to have a lab exam, which I will open on. I'm going to open it on Tuesday. No, can I open it on Tuesday? I can't open it on Tuesday because we won't have talked about everything you need by Tuesday. So I will open it in probably about a week and a half. On the other side of Thanksgiving break sometime. Your lab exam and your final exam are just going to have to be a little closer together than I typically like because we have a Thanksgiving break. But that'll be fine. You can work through it. We're all professionals here. We're all adults, right? Okay. Before I jump into today's lecture, do we have any questions or concerns? Hopes, dreams, favorite stories? No? Anything cool to share? There is nothing cool. Jocelyn is wearing a peppermint sweater. That's cool. That's the cool thing today. It's not December, though? Oh, that's okay. I officially started listening to Christmas music last night. Yeah, I'm sorry. I could not hold it back anymore. I normally wait until Thanksgiving Day itself. I listen to Christmas music for the first time while I make the dinner. I could not hold it in anymore. I needed some Christmas music. So. Huh? Already in the Christmas spirit. Already in the Christmas spirit. Yep. All right. Let's jump in. We cannot start about talk. By the way, Module 3, for those of you that don't remember when I told you this is going to be a play-by-play walkthrough of the history of Earth. Okay, starting at the beginning. Now, how far back is the beginning? Can't talk about the history of Earth without talking about the history of our universe, right? 13.7 billion years ago. As far as we are currently aware, the Big Bang. Now, the Big Bang was essentially, I'm not going to go too deep in on, I'm not going to go all Neil deGrasse Tyson on you here. But the Big Bang was essentially an explosion of fundamental matter. Particles, the simplest element. What is the simplest element? Hydrogen. Hydrogen. Just a whole bunch of hydrogen and neutrons and protons and electrons all flying out of a central point. Now, what caused that explosion? Absolutely nobody knows. Okay? There are plenty of theories. Some people, I just told you I wouldn't go Neil deGrasse Tyson on you, but I'm going to tell you one possible theory that people keep bringing up. A hole from another dimension, perhaps, or another plane of existence of some kind. A hole got torn between that plane and this plane, and where empty space there was here, matter flowed through. And some people theorize that black holes in this universe could potentially be holes torn in our reality, in our dimension, and matter is flowing through those black holes and spewing out into the empty space of another universe on the other side, making its own Big Bang there. Fascinating thought. However it started, whatever caused it, it was an explosion of matter from a central point that expanded outward. Now, this is an incredible amount of matter and energy all contained within a very small area to begin with. Remember, matter cannot be created nor destroyed. It remains constant, right? Matter and energy may switch places every now and then, but the total amount remains constant. The Big Bang was an explosion, an expansion. In the first few seconds of that expansion, all the matter and energy that is in our universe right now was packed into a tiny little area. Incredibly hot. Hot with 40 zeros on the end, right? I can't even remember the number for how big that temperature was that they estimated. And it continued to expand. And as it expands, what happens? Temperatures drop. More heat and matter spread over a larger area equals less heat overall in one location. Same amount of heat. If there was 1 trillion degrees Celsius in the universe when it was this big, when it was as big as a beach ball, that same amount of energy is still present in our universe today, as it is expanded to 13.7 billion light years across. It's just any one location is cooler now. Space is pretty cold, right? However, there's some places like our planet, like Venus, right? Very hot. Same amount of energy is present, though, as there was at the beginning. Now, as all this energy got spread out, all this matter got spread out, some of it would coalesce. Electrostatic draw is what caused this, we believe. What is electrostatic? If you, bless you, have any of you ever done that experiment where you take your hair in a balloon and then your balloon will like stick to the wall or to your hand or to your clothes? You have created an electrostatic field around that balloon by creating that static friction. There is a very small electrostatic charge to everything, including individual atoms. That electrostatic charge caused some of these hydrogens to be drawn to each other. And as more of them became drawn to each other through this initial electrostatic pull, eventually enough mass was in a small enough area, it was in a large enough area that gravity took over. Once you have enough mass in one location, there is gravity, a gravitational effect. Mass, the presence of mass causes the draw. It creates, I guess you could say, a well, okay? A dip in space-time that pulls other things towards itself. Gravity and time and space and how they interact with each other are extremely weird, and we are still learning about it, okay? Gravity, however, we used to kind of think of it as one of those givens, like it's in the background of the universe. It just exists and it is, and it can't be changed, and we can't affect it until we observed 2 black holes colliding in space and watched ripples in gravity affecting the light around this collision. Now, if nature can affect gravity like that, theoretically, so can people. And so observing that, this was back in the early 2010s, observing that caused the scientific community to go into a major uproar. And now there are people studying how we could potentially manipulate gravity ourselves. Very fascinating subject. Regardless, this gravity pulled more and more hydrogen in. As more and more hydrogen got pulled in, what happens? The gravity goes up. It gets bigger, it gets higher, right? And so more stuff gets pulled in until finally you get a cloud of hydrogen that is so dense because of all the hydrogen that it collapses in on itself. Okay? And starts entering a fission and fusion cycle. There is so much energy present in the super dense cloud of hydrogen that hydrogens get ripped apart and stitched back together. Frankenstein's doing his thing inside of this cloud. We no longer call this a cloud. Once this energy starts getting released, this massive amount of energy from fission, ripping apart, and the fusion, the stitching back together, it has entered into a state that we call a star. Now, there are different kinds of stars, okay? I won't go into all those, but they go through life cycles, okay? Stars emit wavelengths of light based upon what they are currently in the process of making, right? In that present moment in time. Our sun is making quite a bit of sodium right now. It is emitting what color of light?
White. No.
You said white. No. What color is our sun? White? Orange, yellow? I'm hearing a couple of options here. What is it? What color of light does our sun put out? I've got a white and an orange and yellow. Who's going to break the tie? Don't be afraid. Come on. Input. Huh? White? White has broken the tie. That is correct. Our sun is emitting white light right now. It is a white star. It appears yellowish to us because those wavelengths get a little bit bent as they go through the atmosphere. And especially during dusk and dawn, when it has more atmosphere to go through, it appears to be more on the red spectrum, right? However, the light that it is putting out is white. If that were not true, snow would be yellow. And then you would never tell which kind not to eat, right? Because snow and other white things are, in fact, white, that tells us, yes, that the wavelengths that the sun are putting out right now are dominantly white. There are blue stars. There are red stars. There are all sorts of stars. No green stars, though. Interestingly enough, yeah. Interesting. White contains pretty much every wavelength of light, though, right? That's why prisms are a thing. You ever seen that effect with a prism where you hold it up to the sun's light and then it separates out the different wavelengths? You got red and blue and yellow and all of that. It's beautiful. We'll talk more about the wavelengths of light that sun puts out and separating those here in the natural world later on in the class. But our star is currently generating a lot of sodium, which means a lot of white light. It'll go through a different phase, though. It will go through different phases. It has been different in the past. It will be different in the future. Given enough time, we estimate maybe another 4 to 5 billion years or so, it will enter its late phase. You can think of our star as being middle-aged right now, young to middle-aged. Eventually, in another 5 billion years, it will enter old age, if you want to think of it like that. It will become what is called a red giant. A red giant it's going to expand outward. It's going to get a lot bigger. Why is it becoming a red giant? Because it's gone through making so many other different elements that it has now entered a phase where it has a lot of iron in it. And so it's going to be putting out a lot of red wavelengths, okay? Iron and other heavier elements. We call this the R process, by the way. A sun generating, creating all of these heavier elements as it goes through its life cycle, gradually making more and more of the heavier elements, increasing in size, expanding outward into a red giant once it hits iron. It's going to get so big, it's going to fill up so much of our solar system that where our Earth's orbit right now is, will be inside of the star. Where Earth is right now will be inside of the star. Whatever is here, if there's anything still living on this planet, will get burned to a crisp. Okay? Hopefully by then we will have moved on. If we haven't moved on in 5 billion years, I don't know that there's that much hope for us. We're all still just here living on our tiny little planet, playing on our Xboxes. We deserve to get burned to a crisp. No. So it's going to get big. And then eventually, after that, the next phase after that is the death of a star. Now, a star dies in a couple of different ways. It can just kind of stop its fission and fusion functions, and it'll cool off, and the gases just kind of disperse quietly, waft away into the universe. Or there's the other option, significantly less quiet. You know what it's called? It's a nova. Yes, a nova. When a star goes nova, that means that it has become so dense. There are so many dense elements in there, like iron, that the core of your star, all of a sudden, the fission and fusion and the constant eruptions and explosions inside of it can no longer hold back the density of all of this matter, and it crushes in on itself. All of a sudden, just the core does, not the outer parts of your star, just the core where these heavy elements are, right? And you get the super, super incredibly dense ball of iron in there, and this happens like that, almost instantaneous. The effect of that incredible quantity of mass super condensing under all of that pressure, under all that gravity, under all that dense compression, creates a gravity wave that radiates outward, blasting the outer parts of your star into the universe. We call this a nova. When a star explodes, we don't talk about this much. There is that little, relatively speaking, right? Probably about the size of Jupiter when all is said and done, ball of incredibly condensed heavy elements like iron that's left behind after a nova. It cools off and it just floats in space. There are these balls of iron that just hang out in space where once there was a star. They're cold, they're dead, we can't see them, but that's what's there, floating around in the middle of what once was a solar system until it gets pulled into something else, gets pulled into a black hole. Maybe it gets pulled into another star, gets melted, reabsorbed, reutilized. The universe uses it in some way, but that's what's left behind. And all of the rest of the elements, the outer parts of your star, get blasted through the galaxy, lending elements to the creation of other stars and planets. This R process is how the elements that make us are made. Each of you are made out of elements. Zara, Claudia, Lydia, Cade, all of you are made from elements that were made in a star billions of years ago. Not our star, some other star, 7, 8, 10, 13 billion years ago, went nova and spread the elements that make your body into the universe. And now billions of years later, those elements have come together and made you. Anything in your body that is not hydrogen was made in a star. You're literally made out of stars. How cool is that? It's pretty cool. I think it's pretty cool. You are one with the universe, right? Buddhist walks up to a hot dog vendor and says, "Make me one with everything." No? Wow, tough crowd today. Not even Aaron laughed at that one. Where's Angel, by the way? Who knows? Okay. All right. So, and then after this process, this is what starts the nebular theory, okay? When you get all of these elements spread out through the universe, they start to collect to make stars. Well, your stars exert gravity. They pull things in towards themselves, but not everything gets pulled into the star. Okay, not everything gets pulled into the star. Instead, some things don't quite make it to the star. They get stuck in a stable orbit. And as they circle that star, they make these asteroid belts and gas belts and ice belts. And eventually, these belts all coalesce and form planets. That's how we got the planets in our solar system. 8 planets in our solar system. Some are rocky. Some are made out of gas. The rocky ones tend to be more towards the middle of our solar system. The gas The gas planets are on the outer edge of the solar system. The heavier, denser material was pulled closer to the star, right? So we have 4 rocky planets close to the star and 4 gas planets on the outer edge of the solar system, right? Okay. This is the nebular theory. You go from a gas nebula to a star that traps materials around it, and those materials coalesce into planets. Questions about that? All right. We can learn a lot about our universe by studying meteorites and asteroids. Okay, why? Because oftentimes these are relics of the early stages of not only our solar system, but our galaxy and our universe itself. Okay, there are a couple of varieties. There are stony meteorites, which are exactly what they sound like. They're made out of rock, which means what? They come from some other planet, some other body at some point. We have an entire asteroid belt made out of stony and metallic meteorites, iron meteorites. Those could only have formed after having been put together in some other planetary body, which means that our asteroid belt is made out of the bits and pieces of other worlds, for the most part, as far as we can tell. Some of them have just kind of come together over time. It's ice that has been floating out in space. Some of them are very carbon rich, which is very interesting. Some of them, like this guy right here, are iron. That's all iron. That gray, that's all iron. This is very heavy. But you know what those kind of goldish, yellowish minerals in there are? That's olivine. Do you remember where we find olivine on Earth?
The mantle.
The mantle. Well done.
And is there only like a few places to get it, right?
It only happens on our planet deep in the mantle. You have to go under the crust to find that much olivine in that much pure iron, which means that this meteorite came from the inside of another planet. How the heck did a meteorite in space, flying through space for who knows how many millions to billions of years, end up on Earth after having been part of the inside of a planet? That planet went kaboom for some reason. It went bye-bye. Most likely scenario, a huge impact. Some massive impact, potentially with another planet, caused a chunk of that planet's interior to fly off into space, probably many chunks. And here's another cool thought. You remember how the moon was formed? Another planet named Theia crashed into early Earth, and the two of them together combined to make our Earth that we have now. What if that's a piece of our old planet? Prior to that collision, they got blasted off into space, made its way through space for billions of years before finally recombining with us again. And now we look at it and we're like, oh, where did this come from? Because it doesn't chemically resemble our own planet, because our own planet is now the combination of two. Fires the imagination. I love it. Now, asteroids are a little more problematic. Comets are huge, by the way. There's a difference between comets and asteroids. You know what that difference is? A comet is generally made out of ice, okay? Mostly ice, and there are huge comets out there. There's a comet out there that we caught glimpses of that, as far as we can tell, is about the size of our sun, floating between, it's way out there, pretty far out in the galaxy. It's pretty far from another solar system. It's just a chunk of ice about the size of our sun. Okay? Huh? But an asteroid, when a comet encounters our atmosphere, it usually evaporates before it can even hit the ground. Okay? The smaller ones. We haven't had a big comet hit our planet in a while. But an asteroid, that's different. Asteroids, those are made out of rock and iron and a little bit of ice, but usually have at least a core of rock and iron, which means that they don't actually melt when they are not completely melt or evaporate away when they hit our atmosphere. They strike, and that makes problems. There have been quite a few of these strikes. As a matter of fact, we have a crater just outside of town from one that happened 63,500 years ago, right? If that landed where it is now today, it would wipe out Midland and Odessa and throw a whole bunch of environmental problems into effect for the entirety of West Texas. Okay, it would be a problem. The asteroid that killed the dinosaurs was a problem, right? Kilometers long, made one of the largest extinctions in history. There have been a lot of impacts, not only on Earth, but on the moon over the billions of years. There are relatively fewer today. Why would that be? First of all, look at the moon. Look at this. I've got a globe of the moon here. Pull this thing up. Okay, look at all of the impact craters on our moon. Our moon has been impacted as much as the Earth has. Why doesn't Earth look like that? Why is Earth not pockmarked with all these craters like the moon is?
Is it because the moon takes the blows?
Well, Earth has gotten struck a lot as well, right? Why doesn't Earth have all of these craters all over its surface like it should? What do we have that the moon does not?
An atmosphere?
Atmosphere, water, biology, all of this. Earth is dynamic. Weathering and erosion. All of these features eventually are removed given enough time. A crater like the one we have outside of town, you can drive out there, and unless I told you there was a crater there, you would not know it was there. And it's only 63,500 years old, right? On Earth, they get wiped away. On the moon, they stay. So there have been a lot of impacts on the Earth and the moon, but very few as time goes on. There was a lot early on and fewer as time goes on. Why is that? All the debris that was floating around in our early solar system got pulled in, and it hit Jupiter, and it hit Earth, and it hit Mars, and it hit the moon. But as time goes on, more of that debris is fewer and farther between because it's gotten pulled out, right? Where our asteroid belt is now, you know that we have an asteroid belt between Mars and the other planets, okay, further out. Between that asteroid, or that asteroid belt exists where normally the gravitational pull of the other planets, of all the planets in our solar system, aren't strong enough typically to pull them towards themselves. There's an exception. I'll talk about that in a minute. But that's why we have an asteroid belt there, okay? It's kind of a gravitational dead zone most of the time. And so that's what our solar system would have looked like billions of years ago. When all of our planets pulled those things into ourselves, right? So that's why we don't get strikes that often anymore. And when we do, they're usually pretty small. However, here's that case I was talking about. Every now and then, the second largest gravitational body in our solar system comes out to play. Do you know what the second largest gravitational body in our solar system is? Well, what's the first largest? The sun, right. Jupiter. Jupiter is the second largest gravitational body in our solar system. And every now and then, its orbit around the sun takes it closer to the asteroid belt. And when it does, it tends to strip a few asteroids out of that asteroid belt. Its gravity pulls them out of that asteroid belt, and then they go zipping around our solar system on these new orbits that we have to calculate and see where they're going to end up. Every now and then that happens. Few wild cards every now and then. One of those wild cards was found decades ago. It is called Apophis. Any of you heard of Apophis? A few decades back, Apophis was found and named Apophis. I'll get back to that name in a minute. But before when they named it, they gave it that name, and then it wasn't until actually not that long ago that they actually bothered to track its trajectory. This is the trajectory of Apophis and Earth. Earth being the blue, Apophis being the purple. Watch what happens in 2029. Right there. You see how our orbits pass? Now, it doesn't go that far, but I'll go further here in a second. When in 2029, Apophis passes close to Earth, it will be closer to Earth than the moon is. Yeah, oh. It's going to be close enough that you will be able to see it without a telescope. You'll just be able to look at the sky and see an asteroid. That's pretty dang close. That's the closest any asteroid this big and dangerous has been to Earth in a very long time. And it has a lot of people concerned. Every time in history, it passes us every now and then. And every time that it has passed us, Earth's gravity pulls it a little bit closer, and we have to remap its trajectory. After the last pass, this was the model that they generated. It's going to be that close. So, this is the question. In the 2029 pass, it's not going to hit us. We know it's not going to hit us. It's just going to get real close. However, the next pass is in 2036. And after the 2029 pass, is it going to be pulled close enough that in 2036 it will hit us? That's the question. There is a hole in space, which is a weird thing to say, but an area in space between Earth and the moon. It's about 400 kilometers wide, I believe. We call it the keyhole. If Apophis goes through the keyhole in 2029, it will hit Earth in 2036. That's what we're watching for right now. All the space agencies are gearing up to do something about it. I'll talk more about that in a minute. If it does go through the keyhole, it will hit Earth in 2036 off the coast of Hawaii. It is large enough that it will make a tsunami several hundred feet tall, put a cloud of ash in the atmosphere once it hits the ocean's bottom. It's not going to create an extinction level event, but it will wipe out Hawaii and all the other Pacific islands. It will destroy pretty much every city on every Pacific coast: California, Alaska, Argentina, Chile, Japan. We're talking millions and millions of people, which is why world governments are very concerned about this. And some of the infrastructure that they have been putting together is specifically to deflect Apophis. If it does go through the keyhole, then before 2036 rolls around, multiple space agencies will have infrastructure out there to deflect it. What can you do? What do the movies do whenever they need to take care of an asteroid? They blow it up. Why will that not work? Right, it could make a bigger problem. You make a bunch of smaller pieces, but also, what do you need for things to actually blow up? You think about watching Star Wars, right? You're watching Star Wars, or you're watching Star Trek or something, and you pew, 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 and the spaceships blow up and there's fire everywhere. Why does that not make sense? What do you need to have fire? What do you need for an explosion? Atmosphere. There's no atmosphere in space. You can't blow things up in space. Things disintegrate in space. There's no atmosphere to facilitate an explosion. So yeah, you can't really blow it up. We could launch a nuke at it and hope that the sheer quantity of radiation from that nuke melts it, or if there's some ice, degasses that ice, like causes that ice to flash vaporize, and that instant flash vaporization of the ice propels it in a certain direction. But we have no way of knowing what that direction would be. Yeah. No, they wouldn't be bigger in space. What would be, there would be no explosion. There would be a flash of light from the initial reaction inside of the nuclear chamber. But then all you would see is radiation. Some of it would be visible, some of it would not. but it would be incredibly intense because there's no atmosphere to deflect and subdue the radiation. So nukes in space are significantly more dangerous than they are on the planet, really, when you think about it, because that is massive quantities of hard radiation that get spread out in every direction, okay? Which means it's extremely difficult to use a nuke to deflect something like a comet or an asteroid because you have no idea of predicting how that radiation is going to affect that body and where its new direction will be, what its new path will be. Instead, what they have been developing are more like kinetic launchers. Think of it like a gun. We launch something, probably from the moon, or from a space station or a satellite, that is intended to have a lot of velocity. Because there's no atmosphere in space, there's nothing to reduce that velocity, okay? So if you shoot a chunk of metal, like a bullet, at just the right moment so that it intersects Apophis at just the right plane of its orbit, then Apophis will absorb that energy and get shoved in that direction, right? Into what hopefully is a predictable orbit path. This is the technology that multiple agencies have been developing. They actually tested something like this on a smaller asteroid 2 years ago, and it worked pretty well. They just need to scale it up to fit something like Apophis and then get their math just right so that what you want to do is you want to do this far enough in advance. You want to shoot this thing far enough in advance that if you miss, you have at least a few other opportunities to get it right. Because if you wait until the last minute to hit it and then you miss, sorry, Hawaii, right? So, asteroids, comets, very relevant to our society. Most people don't even know about it. Most people have no idea that this is a possibility, right? Look at that. You come to my class, you learn all the ways you can die. Asteroids, volcanoes, earthquakes. What a fun time we have, right? Okay. Now that we have covered all of that, let's talk about the actual formation of the Earth. Through the nebular theory, we've learned that these loose particles, these loose solid particles come together and form early planets. These early planets were really, really hot. Think ball of melted rock hot, right? Initially. Why? They're constantly getting pelted by new asteroids, possibly even other planets, slamming into each other, keeping them in a semi-melted or totally melted state at times, right? Adding mass, adding new exotic particles, new things, new radioactive elements, okay? Keeping things hot. As time goes on, things start to cool off. You form a crust. Differentiation. You guys remember Bowen's reaction series? Okay. Differentiation of elements as magma cools off. This starts to happen, meaning that your lighter elements start to form on the outside of your ball of melted rock. You get this early crust, and your heavier, denser radioactive elements typically sink further into the middle. You get this differentiation of layers. So we have an early crust, an early mantle, an early core, right? We call this the Hadean, okay? Hadean after Hades, the Greek underworld, right? Hot, hell, think hell, right? That's why it's called that, okay? So the Hadean, 4.54 to 4 billion years ago, early Earth formation, absolutely nothing alive at this point, right? By the way, also, Earth gets struck by that other planet, right? Theia, moon is formed, all of that. It has to reconsolidate, reforms, okay? So at the end of the Hadean is the Archean. Now it's in the Archean that we start to see the first forms of life. And then the Proterozoic, that's when life really starts to take off. We'll talk about all that in time. But these are the bottom 3 sections of our periodic table, or not periodic table, of our geologic timetable, okay? All collectively referred to as the Precambrian. So the Hadean to the end of the Proterozoic is 4 billion years of history. That's 4 billion years right there that we're talking about today. And then for the rest of Module 3, we're talking about the next 500 million. Okay? We're covering 4 billion years of history today. So in the Hadean, a few things happened that we already talked about. The two planets collided, making our moon. We got the differentiation of the layers as the denser elements sink towards the middle and the lighter elements are differentiated towards the top, making our crust. Come on. You can do it. You can. I don't know. Can you do it? And it skipped. Okay, here we go. So our early ocean started to form during the Hadean. At the very end of the Hadean, we believe is when the ocean started to form. What was making our ocean? Don't look. What was making our water?
An atmosphere.
We didn't have atmosphere, at least not in the same way that we do now. We'll talk about that in a minute.
Melted comets?
Comet impact. What are comets mostly made out of? Ice. So yes, we get stuff hitting our planet, bringing with it water. There is so much water in space, my friends. Matter of fact, water, H2O, from what we can see looking out at space and collecting the wavelengths of light that bounce back at us, water is the most common three-element particle in space. It is everywhere. Thinking that Earth is unique because it has water, it's not. So many other places, planets, have water. It's pretty cool. But yeah, we get all this water. That water, yes, does account for a lot of what goes into making our oceans, but also volcanic activity. What is one of the most common gases expelled from a volcanic eruption? H2O, right? Water is one of the natural byproducts, one of the volatiles produced when magma comes up to the surface. Okay? Now, our atmosphere initially looked nothing like what our atmosphere does today. High in ammonia, high in hydrochloric acid, probably methane, right? You would not be able to breathe this. One breath of this, you melt your lungs. Okay? Very caustic. However, it did set the stage for life to begin because it is in this environment with very little free oxygen that we can conduct experiments and realize with a little bit of electricity and this particular recipe of gases, you start to form amino acids. Those amino acids start to form early DNA. Each one of these amino acids in this DNA strand can be made in that environment. We've tested it. We know it's true. Matter of fact, I think I told you this before, we can see some of these amino acids in space, right? We can see that they are present in space because they can form in environments with absolutely no biological context, okay? No organic context even. This was an inorganic environment that ended up making organic products. It's pretty cool. Okay. Okay, so we start to see the earliest proto-continents form. What is a continent? Remember, a continent forms whenever there is a mountain building event. What does mountain building happen? When you have tectonics, right? So tectonic plates started to move. We think that maybe it could have been potentially a byproduct of that collision that Earth had with the other planet. That is not confirmed. As far as we can tell, tectonics seems unique to Earth. Mars has no tectonics. Venus, from what we can see, has no tectonics. As a matter of fact, if Venus had tectonics, it probably would not be in the situation it is right now with the greenhouse gas effect. Tectonics on our planet does a lot of cycling, particular carbon cycling. Without tectonics, we would have a lot more carbon in our atmosphere, and we might look like Venus, right? So Earth has tectonics, and other planets that we can see do not. Very interesting indeed. But because we have tectonics, we got the development of continents coming up out of the early oceans. These highlands popping up out of the oceans were mountain belts initially, and then a mountain belt will crash into another mountain belt and make a larger body of land. And these are what we call protocontinents. Now on this map, you can see all of these gray areas. That's exposed Precambrian rock. All of the beige areas, those are buried Precambrian rock. All that Precambrian rock was made in this protocontinent to continent transition that is happening now, or I should say during this time period. Okay. That's the Hadean. That's pretty much all that's happening. Okay. Atmosphere developing, oceans developing, continents forming, collisions still happening. Every time there's a major collision, excuse me. Every time there's a major collision, kind of sets the clock back a little bit as far as things developing. In particular, life. Without major collisions, who knows how much earlier life could have begun? Without some of those major collisions, who knows if life would have begun at all? There are asteroids out in the asteroid belt that are almost entirely made out of carbon, from what we can see. Maybe early Earth was low in carbon until a couple of those asteroids hit us. Don't know. The Archean. At this point, we've got a series of microcontinents. Remember in that, that model I showed you a few weeks back, where you saw the video of the continents forming and reforming and changing and colliding and making the supercontinents? Early on, you saw that there were a whole bunch of tiny little islands, what looked like island chains. I'm calling those microcontinents, okay? So there were a lot of them scattered all over the surface of the planet. During the Archean, the crust generation really went into overdrive. As a matter of fact, it's by the end of the Archean that we believe we had about the same quantity of continental material as we do now, which means that it went real fast. There was a lot of continental generation. Why that happened, I couldn't really tell you, other than it was probably a lot of convection activity causing a lot of magma to come up to the surface. A lot of magma approaches the surface. There's a lot of Bowen's reaction series generating a lot of continental material. Okay. Something inside of the planet spurred on this. Maybe it was just the development of more convection cells as Earth continued differentiating on the inside. Seems like the most likely scenario to me, but I couldn't tell you if that's accurate. Greenstone belts. These are relics, I guess you could say, of this time period. Think that at this point in time, during the Hadean and the Archean, at least the beginning of the Archean, there is very little free oxygen. Oxygen is very reactive. It binds with a lot of stuff. You know that term we use all the time, oxidization, right? We use that to describe the process by which oxygen binds to a thing, and usually it transforms into something else, right? Oxidization of iron makes it red. We call it rust, right? Makes it ferric or ferrous oxide, depending on the situation. Then you've got sulfur oxides and dioxides. You've got copper will tarnish green with oxygen, right? So greenstone is a mineral that is on its own naturally green. And without the presence of oxygen, transforming minerals into other colors, chlorite, this green mineral, formed a lot of the structure, a lot of the content of the mountain belts at this point in time. So you get metamorphic mountain belts made out of a lot of chlorite. And so these ancient Archean mountain belts are called greenstone belts. I actually have a chunk of greenstone from Canada. There's a large exposed section of a greenstone belt in Canada. So my sample is about 3.1 to 3.2 billion years old, I believe. Something like that. And then there's another belt in South Africa I'd love to go to sometime called the Barberton Greenstone Belt. I'd love to go get a sample from there sometime. It's pretty old. And then there's lots of exposed ancient rock in Australia as well. Let's see. Now, why do we believe that life began in the Archean? Well, remember what I just told you about oxygen. What does oxygen do to iron? Makes it rust. And what color is rust? Red. So we start to see in layers of deposited iron that at various points in time, that iron is red, which means that there's the presence of what?
Oxygen.
Oxygen. Iron will not go red without oxygen to make it do so. What is the most likely scenario for the production of free oxygen? Chemosynthesis,
Yeah.
photosynthesis, all these syntheses, right? These metabolisms that the byproduct of which is the formation of free oxygen. The development of some living thing, probably beginning with chemosynthesis before moving on to photosynthesis later on. Now, as these early, we'll call them bacteria, or archaea, technically, we believe is the first one, okay? Which is why the time period is called the Archean. As these early archaea and bacteria started to form in the oceans and started to chemosynthetically break down sulfur dioxides and carbon dioxides and these other molecules, these other gases and liquids that they needed subparts of, but they didn't need the oxygen, they would release that oxygen. That oxygen would bubble up out of the water, enter the atmosphere, oxidize the iron that's being deposited in the water, and you get these layers of red. We call these banded iron formations, BIFs, if you will. And I have one right here. This is a banded iron formation. The earliest evidence that we have of life. No fossils. Just this. The only logical conclusion for where this free oxygen came from, chemosynthetic life forms. It's pretty cool. I'll actually pass this around. Now, our continents started getting real big about 2.7 billion years ago. We're going to start seeing supercontinent activity here pretty soon. I'll let you know when. By the way, that leads me to an important note. It may be worth your time, wink, wink, to keep careful track of when I say supercontinents are and when major mountain building events occur. And that's all I'll say. Okay, now, the Archean, while there is plenty of BIFs to suggest that there was life, again, we do not really have any fossils from that time period. Some, but not a lot, towards the end. Mostly just kind of things like stromatolites towards the end are what we're seeing. And they were prokaryotic, right? Now, where did this life begin? Well, mid-ocean ridges, from what we can tell. And the main reason why mid-ocean ridges has to do with those black smokers. Do you remember what the black smoker is? I showed you a picture of it a few times.
Huge things at the bottom of the ocean just spewing out chemicals constantly.
Yeah, it's a vent at the bottom of the ocean near these mid-ocean ridges. And through this vent, it looks like a whole bunch of dark smoke is coming out and kind of spreading through the water. It's not smoke at all. Do you remember what it is? Iron and other metals that have been dissolved out of the hot, newly formed rock down there where the crust is shallow and the water is brought up to the surface. It's super hot water. When it hits that cold water at the bottom of the ocean after it comes out of the vent, all that metal precipitates out, falls to the bottom. What a beautiful element-rich environment for something that chemosynthetically strips metals out. What a beautiful place for that, for organisms like that to live. As a matter of fact, there's still tons and tons of chemosynthetic organisms that live around these vents. They've sent rovers and drones down there. We can see huge colonies of bacteria and other organisms that are thriving off of that process, chemosynthetic process. This is significant in a few ways. First of all, we believe that's where life began on our planet, around these vents, where those early chemosynthesizers found plenty of nutrition to survive. There's another thing, though, and I'm curious to know if any of you can figure it out. Does this imply anything for life anywhere else? Could the existence of these chemosynthetic organisms living at the bottom of the ocean imply anything for life anywhere else?
It implies that there could be life somewhere else. We just can't see it yet.
There definitely could be life somewhere else. And yes, we wouldn't be able to see it, but why? Huh?
Like at the bottom of the ocean.
Do these organisms at this point require light? No. They're not photosynthetic yet. Yeah. I did not. Can we come back to that in a minute? Okay. There are places in our solar system, Enceladus, Titan, Europa, ice on the outside, layer of water, and then a solid, hot inner core, keeping some of that water liquid. The fact that this life developed at our mid-ocean ridges without the need for light and having these things live and die for billions of years at the bottom of the ocean, still do, without ever having seen a single ray of light. These moons that I just mentioned, Enceladus, Titan, Europa, just to name a few, the potential for chemosynthetic life to exist inside of the planet where light never penetrates, I mean, come on. Hugely possible because it happened here, right? Water, chemical bonds that can be broken, and nutrition and energy gained through that process. Very possible. So, what were you saying? I did not hear anything about aliens in the ocean. Enlighten me.
I don't know if it's real or not. But like they said that the UFOs that were spotted recently are from like aliens in the ocean.
Oh, the UFOs are from aliens in the ocean?
Yeah, they said that they're trying to reverse engineer the technology they use or something like that. Just want to get your thoughts on that.
Are like suggesting that they set up a base in the ocean or that they live in the ocean?
I'm not sure.
Because technically, I mean, if they're from the ocean, they're not aliens, are they?
Yeah.
It's like if we ever discovered, I don't know, like in how Aquaman in the DC universe, his people live in the ocean. They're not aliens, right? I mean, the term alien is scalable. We use the term aliens to describe people who come to a country from another country, for example. We're in the same species, but they can still be referred to as aliens because they are foreign to that particular location. The alien, as in the context that you're describing, though, they would need to come from another planet, right? They would need to originate from another location. But if they developed in the ocean, if they're fish people, right? They're not human, but they're earthlings like the rest of us. There's all sorts of crazy things that I hear from the alien community. I 100% believe that there are aliens. Have I told you the math about why I believe there are aliens? No? Tangent. Let's assume, keeping with our current rate of colonization into civilization, that if we went to space flight from forming civilization in about 20,000 years. Okay? Earliest civilizations to leaving our planet took about 20,000 years. If we assume that same process, hold that math, hold that number, okay? We send some colonization ship to another world. That world, the closest planet that we believe is habitable without terraforming, is about 4.5 light years away. Okay? It's in the next galaxy over. Just from what we can see of that planet, it's in the same distance from the sun that our planet is. It has water. It has atmosphere. We don't know what the chemistry of either of those things are, but it appears to be very Earth-like. That's the closest Earth-like planet that we know, about 4.5 light years away. It would only take us 4.5 years to get there if we could travel at the speed of light, but we can't. Right now, the best we could probably manage, if we pulled all our resources together and made just the right ship with just the right engine, we could probably propel something to about 10% the speed of light. Okay, so if we propel something at 10% the speed of light towards that planet, how long will it take them to get there?
45 years.
45 years? Do we agree with that? Yes, it would take 45 years to get there. Okay, so 45 years there, that's a whole generation. Those people will be, if we send them as teenagers or young people, they'll be old when they get there, right? Their kids will be the ones that really benefit from getting there. And a trip back, out of the question, right? Who would even want to come back? Their grandkids would be old when they got back. And how do you even send them back? Do you have enough fuel? Probably not. Probably burned up whatever fuel you had on your trip there. It's a one-way trip is my point. And what do they have when they get there? Only what they take with them. Considering that what you take with them increases your mass, and the more mass you have, the more fuel you need to burn to reach those speeds, you want to take as little as possible. Therefore, my argument is when those people arrive, they have to start civilization over again. They might have a few things, farming tools, stuff like that, maybe some construction equipment, but how long does that stuff last? Not long. Maybe enough to build a few communities before it breaks down and can't get repaired. You have to start civilization over again. You can't take civilization with you wherever you go. So assuming that same number of 20,000 years, okay, for that new civilization, that colony, 4.5 light years away from Earth, 20,000 years later, they once again achieve spaceflight capability and send their own colony ships out. Okay? At that rate of progress, 20,000, 20,000, 20,000 between waves of colonization from each world, our galaxy would be populated by humans in about 300 million years at that rate of expansion. Our universe is a lot older than that. Our galaxy is a lot older than that. So where are the aliens? If our universe can be populated at that rate in 300 million years, and it's a lot older than 300 million years, where is everyone? This is where the problem comes in. There are a few arguments. There is one group of people that say humanity and every other intelligent species are doomed to annihilate themselves. Once they reach the nuclear age, they annihilate themselves. I don't like that theory. That's not very fun. And then there's the ascension theory, that humanity is teetering on the edge of reaching a point where we can ascend our own physical plane of existence. We know so much about digital, for example, and we are right on the edge of understanding multi-dimensions, other dimensions, other planes. We can observe, interact to an extent with the possibility of these things, right? What if, and this is what ascensionists believe, Intelligent civilizations are not destined to destroy themselves, but are destined to leave the material world behind. There is even a smaller group of those people who believe that black holes, being the super dense disks of matter that they are essentially refuges where ascended individuals, ascended species, groups ultimately end up. Think of a black hole as essentially a super dense, super compact dimension in and of itself. Think of it as like a hard drive. There are all sorts of crazy, I say crazy, but who knows, right? Theories like that. But my point is, where is everyone? If humanity could do this mathematically in 300 million years, are we the first ones? In 13.7 billion years, that does not sound likely. Or are they just leaving us alone? Or is it happening right now? Could we go out to that planet 4.5 light years away eventually and realize it's already been populated? Yes. Unwelcome visitors from another world? Oh, shoot them out of the sky. Or say, hey, sorry, man, this planet's taken. Go somewhere else. That's entirely possible. There could be massive expanding alien empires right now. We don't know. That's the stuff of science fiction right now. Someday it may just be science. Could be true. But that's the biggest problem. The math doesn't add up. There should be aliens everywhere, according to the math. I do believe they exist. It's statistically so incredibly unlikely that they do not. But as to why they aren't all over the place and why we haven't encountered them yet, officially anyway, don't know. Interesting though, huh? Questions about that? Any further discussion?
You figure that it have to with like the experiments we've done.
What sort of experiments?
The one to get like, what is it? The one they conducted in space with the elements to get, what was it, RNA?
I'm not sure what experiment you're referring to though.
Like the one we were talking about earlier, like where they conducted the experiment in space with
The gas.
I don't remember. Yeah, gas.
Oh, you're talking about the Miller-Urey experiment, where they made amino acids. Okay, they didn't make RNA. They made amino acids, which can then go on to form RNAs, right? Given enough time in the right situations, right? The Miller-Urey experiment proved that life could develop in situations that we assumed it could not before. Basically outside of what we call the Goldilocks zone. Remember that Goldilocks zone outside of every star is between where the water on that planet is between 0 and 100 degrees Celsius? We assumed liquid water was required for life. But the Miller-Urey experiment proved that no, it really doesn't, right? That life could exist in other places regardless of the quantity of fresh water or liquid water there, right? So it expanded out what our bounds, what our thought process for where life could be is. So who even knows if we would recognize an alien if we saw one, right? There's a book that I absolutely love, and they're actually making a movie out of it. It's called Project Hail Mary. It's by Andy Weir. It's the same guy that wrote The Martian, okay? He does such good work investigating his science. But he encounters an alien. Spoilers, I guess, if you're going to read the book. But sorry, mute me for the next little bit if you're planning on reading that book. But he encounters an alien that is lithology-based. Their entire group, their civilization, they are organisms based on minerals, not biology. Intelligent, but instead of having organic processes that control the functions of their bodies, it's chemical interactions between minerals and various other things in their bodies, passing electric charges through mineral lattices and frameworks and stuff like that to create intelligence. It's a very fascinating concept. But who would even know if we recognized an alien if we saw one, right? We tend to humanize aliens a lot. 4 arms, 4 legs, head, 2 eyes, right? That's just what's cheaper for TV to show. Even the concept that they could have things like tentacles or anything like an eye at all. Maybe they sense electricity. Maybe they sense through, I don't know, air pressure changes in atmosphere. Who knows? We tend to humanize a lot our concept of what aliens could look like. Maybe they don't even exist, or maybe they don't live in a wavelength of light that we could even observe. To us, they'd be visible. Perhaps to them, we are invisible. We pass each other like ships in the night. So many possibilities for the ways that life could develop. Okay, let's move on. Towards the end of the Archean, reefs of stromatolites are forming. Okay, very, very successful. These stromatolites are becoming these colonies of these algae, of archaea and bacteria. Okay, becoming so successful that they're forming reefs in the ocean, huge communities. Okay. Now, for the Proterozoic, we have a lot more data for that. Why? Because it's more recent and therefore more geological evidence, but also more life and therefore more fossil evidence for the things that went on then as well. Okay, so this is the first mountain building event, or orogeny, that I mentioned you may want to take careful track of. Wink, wink. Okay, I don't know how much more obvious I can make that. The Wapmi orogeny happened in the Proterozoic. The Wapmi orogeny, this is the first major mountain building event that has to do with North America. I'm only going to tell you about orogenies that have to do with North America. If I went through every orogeny that was significant in the history of the world, we would literally be here all year. So instead, we're only doing the major ones that are significant to where we live, North America. Okay, Wapmi orogeny, 2 billion years old. You can find the evidence of this west of Hudson Bay in Canada. Okay, this happened when an island chain ran into what was called the slave craton. Okay, remember, a craton is what's left of an ancient microcontinent. So an island chain ran into the slave craton. They crashed into each other and made a mountain range that came up high out of the ocean. And the remains of that are out here in northern Canada, right there. Okay, this is the Wapmi orogeny. During the Proterozoic, Earth got very cold. Tell me why. What could have happened that we just recently talked about that could make the Earth very cold?
The bacteria eating all the carbon, essentially. And
The-
the Earth getting colder because of that.
Yeah, the bacteria, they're doing their thing. Initially chemosynthetic, but at this point, photosynthetic, right? What are they doing? They're absorbing greenhouse gases out of the atmosphere, primarily carbon dioxides. What are they doing? They're taking the carbon, stripping off the oxygen, spitting it back out, saying, I don't want that, right? And so our atmosphere is becoming depleted in greenhouse gases and enriched in O2. O2, that doesn't stop nothing, right? And so as a result, temperatures drop, snowline drops, more glaciers, more reflected light, less heat, snowline drops, glaciers develop, all of this, okay? Positive feedback loop. And it was so intense, this was such a profound effect that it made what we call snowball Earth, which I'll talk to you more about here in a minute. Man, I got something in there. We see for the first time a distinct diversification that we can track and we can see in the types of stromatolites that are forming. Actual different groups that prefer different things like different salinities, different climates, different depths of water, things like that. We see a big diversification in stromatolite communities. And we see the first strong evidence of eukaryotic life. How did this happen? Prokaryotic cell, eaten, a producer cell, I should say, eaten by a larger cell, a consumer cell. They start working together. And here we go, boom, bada boom. It's like a synonym for participating. What do you, working together?
Collaborating.
Yeah, collaborating works. That's not the word I'm looking for, but it's better than participating. Thank you. Two cells that are collaborating together, right? Huh? Not uniting. One joined the other and they started working together to form a more efficient, huh? Symbiotic is an excellent word for that. Symbiosis, okay? Two symbiotic organisms that come together, they work together and make a more efficient organism as a result. Okay? That started with just two cells, a producer cell, a consumer cell. Producer cell brought the ability to provide energy to the party. The consumer cell brought protection and a larger body, right? And together, they were able to work to the point that multicellular life began. Okay? And this is where we start to see actual chains of cells, okay? This coiled ribbon here, that's an algae fossil. That's an algae organism. And each one of these, by the way, this string is cell, 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 just a daisy chain of cells that are all working together here, okay? You can see that better right here. This is an amoeba. And you can see that each one of these segments here, that's its own cell. And each in this daisy chain, they are working together to perform a function. The function of those is different from the function of these. It's different from the function there, okay? All of these are different, contain different functions. So 750 million years ago, we start to see complex amoebas like that. 650 million years ago is when we start to see these guys. Near as we can tell, these seem to be early forms of sponge. Okay, not the same sort of sponge that we have now, ancestral to that, where they were living on their own in these structures. And eventually they would form these colonial groups that we see today. The Ediacaran began 570 million years ago. It is during the Ediacaran that we start to see incredibly complex, well-formed fossils like this. I know what you're thinking. You're like, wait, that's clearly a leaf. There were no leaves back then. There were no plants. That's an animal of some kind. This kind of looks like a sand dollar. That looks like a worm or like an arthropod of some kind. These are the most well-preserved, and most of these are soft-bodied, by the way. This is some of the most well-preserved fossils that we have from back then. And it's because of these fossils that people want to push the beginning of the Cambrian back to 570 million years, because we found these. Currently, the Cambrian is at 541 million years, because that's where the previous evidence of complex life like this began. So that's in the works. I don't know if it'll happen, maybe one day. But for now, we just call this the Ediacaran fauna, okay? How it jumped from those basic sponges and bacteria to this, don't know. We're missing that transition. There has to be somewhere, and hopefully we can find the fossil evidence for it. However, the lack of hard parts in these organisms makes it difficult. There's some skeletal material, but for the most part, these are very soft-bodied organisms. So I mentioned to you something called snowball Earth. The earliest ice age that we know about, glacial period, was that 2 billion year old one that we talked about. But as time goes on, things gradually get worse and worse and worse until about 750 million years ago, we hit that snowball Earth I talked about, where it got so cold that almost the entire surface of the Earth was covered in ice. Aside from a few strips here and there near the equator, where the water was liquid and stuff could live. Things could survive. And then finally, thanks to volcanic activity and a death of a lot of the things producing oxygen, greenhouse gases built back up in the atmosphere, and things warmed up, and we got out of snowball Earth. So all these microcontinents are piling on top of each other during all this time. As they pile on top of each other, our continents get bigger. Continents get bigger. You get more elevation. More elevation, you get more ice that can form, and that contributed to the whole glacial cycle situation. Okay, from 1.95 to 1.85 billion years ago was a supercontinent called Laurentia, which is made out of the landmass that we currently call North America and Greenland. We will see the development of Laurentia come back together a few times. North America and Greenland are really big fans of each other because they come together and then they separate, and they come together and they separate, and they come together and then they separate, right? Kind of sounds like my uncle's marriage. Ooh, bad joke. Okay. We see the evidence of this over and over again in the Canadian Shield. Okay, so we can see where they were connected here, and then there was some separated, and so there's some sediment that showed up between them, and then they came together again, and so this is kind of like they're piled on top of each other over and over and over again. The continent of supercontinent of Nuna lasted for about 400 million years ago, from 1.8 to 1.4, and this is down here. Was a whole bunch of microcontinents that came together, okay? What is currently India, South Africa, Laurentia, which remember is those two combined, Antarctica over here, South America here, Baltica, which is a big chunk of Europe. This is Australia right there. That's North China, here's Siberia, okay? All of this came together and formed the supercontinent of Nuna. After Nuna was Rodinia from 900 to 630 million years ago. Rodinia included Australia, China, Antarctica, and Laurentia right there, which means that some other things went off and had their own party for a while, okay? Rodinia broke up, and we got Pannonia from 625 to 550 million years ago. Pannonia was Laurentia, Africa, Baltica, and South America. So here, Australia, China, and Antarctica went off and had their own party, and all the things that had left the party before it came back and had a party with Laurentia. Okay, so you're saying, all right, you guys go for a while, and then you guys come back over here. Okay, you guys go back for a while, and then you guys come back over here. It's just kind of wherever the tectonic directions were going, it's just funny that it ends up that some of them are never in the same party, and some of them, you know, I don't know. That's just the way I think about it. It's like, maybe that's weird. Gondwanaland was mostly Africa. Africa made a huge chunk of Gondwanaland. Matter of fact, to this day, when geologists think Gondwanaland, they think, oh, okay, Africa, because most of that rock is currently in Africa today. Okay, so here you can see how much of Africa took up Gondwanaland. Laurentia was not at that party. It was pretty close, but it was hanging out over here. Antarctica, that's Baltica, Siberia. South America and Africa made up most of Gondwanaland. And that ended 550 million years ago. Or it started 550 million years ago. And then it'll end during the Cambrian, which we will talk about in our next lecture. The Grenville orogeny, another mountain building event, 1.1 billion years ago. We have Laurentia. Laurentia being North America and Greenland combined, right? So here what happened was a whole bunch of microcontinent and island arcs got scraped up onto the south edge. Let me back up here so I can show you. Yes, right here, okay? This section, this stripy section here, that's the future Grenville orogeny. They were nice and they really labeled it for us, okay? That's all the material that got shoved up onto Laurentia later on. It's not there during this. They just have it there to show you how much it would add later on, okay? So it's going to scrape up onto there and add to the overall mass of Laurentia. All of these continents are going to get bigger as time goes on. Why? Because every time they come together, they increase the overall landmass. And every time they separate, they take a little bit of that with them. So what you're going to see is as time goes on, each one of these little microcontinents that comes together and makes these supercontinents, they're going to get bigger over time until you end up with about the same landmass that we have today. You can even see that happening now. Look at this. Look how big Laurentia is here. and it's getting bigger here. And then when you see it in the next time, it'll look even bigger because the Grenville will have fully happened. Okay, but that's the Grenville orogeny. It added a lot of mass to the southern coast of Laurentia. One of the largest asteroid impacts that we know of occurred during this time, 1.85 billion years ago. This is the Sudbury impact. It is right here in Ontario. This is where the crater's at. This impact was so huge and so violent that it picked up chunks of the Earth's crust and threw them 800 kilometers away. There are chunks of Canada from here that are all the way over there because of this impact. Okay? Think about how big that must have been. We watched 2012 for a movie night last semester, right? Do you remember when Yellowstone erupted and there were big chunks of Wyoming that were flying up into the sky with grass and trees and stuff on them and then landing? Think like that, but much, much, much bigger. Chunks of this ended up over here. It made a hole so big and hot that the mantle came up to the surface in that crater before it cooled off. It cooled off pretty quick. The mantle's hot and it's cold up here, but it cooled off pretty quick. And actually, because of that impact and because the mantle is so close to the surface up there, there are about 8 major mining companies that have set up inside of this crater because they can get to mantle material so much easier than anywhere else. And there's a lot of very good metals that we need in there. And so there are some quite a few major mining operations at the Sudbury crater. All right, well, that is the Precambrian, my friends. Any questions? Yeah.
So what's the oldest rock you have here?
The oldest rock I have is that chunk of greenstone. So about 3.1 to 3.2 billion. It's in my collection somewhere. I don't know. I never actually really unpacked my whole collection of rocks here. I only pulled out the stuff that I use all the time. I don't have enough room to put it all. How much stuff do I have? A lot. I've got about 14 more boxes in that storeroom back there that I've never unpacked. Yeah. It always made a delight to move. Any other questions? Okay. Well, then I will end the recording here. If any of my online students have any questions, you know, you can always reach out to me through email, and I'll get back to you as soon as I can.